Here we will consider exponential distribution. This exponential distribution is another probability distribution dealing with continuous random variables. In this case, the random variable representing the waiting time for occurrence of certain event is considered. For example, suppose a manufacturer of an electronic device knows from his past experience that the product has an average lifetime K years. Suppose a customer purchases this product and from the time of installation onwards, he is waiting for this occurrence of the failure of that unit. Then the time for failure of the unit is considered as a random variable following exponential distribution. Therefore, the probable distribution of x is according to the exponential distribution, and this therefore exponential distribution can be used to model the probability behavior of random variables representing this lifetime of a unit or the waiting time for occurrence of certain outcomes. Now you can see that it is a continuous analog of a geometric distribution. This geometric distribution is another probability distribution in coming in the section of discrete distributions. This exponential distribution is the continuous analog of geometric distribution. Now it has a lot of importance in this in the sense of reliability theory. A property called lack of memory properties makes a powerful tool in reliability theory. Now we come to the definition of this random variable following exponential distribution. A non-negative continuous random variable x is said to follow exponential distribution if its probability density function is f of x equals m e raised to minus mx dx. Here the range of variation of the variable is greater than or equal to 0. That's why we say a non-negative continuous random variable. Moreover, the range of variation is continuous. That means 0 onwards the values are taken by, the variable takes the value 0 onwards. So if you take the total real line, the variation of a random variable, that is from minus infinity to plus infinity. Here, this random variable following exponential distribution can take values from 0 to infinity. That is, all values in the non-negative side can be assumed by a random variable following exponential distribution. In the above example we discussed, that is the lifetime of certain device, the time of installation itself, the product may be fused. That is 0. Now 0 onwards for any time that unit will function. That's why 0 x greater than or equal to 0. Now that is the range of variation of a random variable following exponential distribution. Now regarding the constant, there is only one constant in the exponential distribution, that is m, and it is assumed to be greater than 0. So this equation of exponential distribution is m e raised to minus mx, very simple equation, and its range of variation of the variable is greater than or equal to 0. We denote a random variable following exponential distribution using the notation x follows expm. That is, we are addressing the equation in terms of its constant. Now, when we come to various properties of exponential distribution, first of all, note that this variable has non-negative values, that is, non-negative continuous random variable. Now, regarding the moments, we have a general equation for row moments, that is mu r dash equals expectation of x power r, which is r factorial by m power r. We can derive it as r factorial by m power r. We are not coming to the various steps of derivation of these moments. R factorial means it is the product of 1, then 2, then 3, etc. up to r. So the product of first r natural numbers comes in r factorial divided by m raised to r. So this is a general equation for getting row moments of exponential distribution. So when we put r equals 1, we get mu1 dash. Mu1 dash is the mean. That is mu1 dash is 1, r is 1 here. So 1 factorial. 1 factorial is 1 factorial divided by m. That is 1 factorial is 1 itself. So it is 1 by m. Therefore, the mean of exponential distribution is 1 by m. Likewise, when r equals 2, we get mu2 dash. Mu2 dash is 2 factorial, that is by putting r2 here, 2 factorial by m square. 2 factorial means 2 by m square, 2 factorial by m square. 2 factorial means 1 into 2 divided by m square, that is 2 by m square. Therefore, this second row moment mu2 dash is 2 by m square. Now the variance of exponential distribution is given by mu2. Mu2 is e of x square minus, that is mu2, that is the variance of x, that is equal to mu2 dash minus mu1 dash whole square, or in terms of expectation it is e of x square minus e of x whole square, that is 2 by m square minus 1 by m square, that is 1 by m square. We can see a common denominator m square, so 1 by m square. Standard deviation of x is the square root of variance of x, which is 1 by m. So you can also note that in exponential distribution with constant m, mean and standard deviations are equal to 1 by m. Now let us see the third and fourth row moments, and also from those the third and fourth central moments. So they are obtained by putting r equals 3 and 4 in these equations. So when r is 3, it is 3 factorial by m raised to 3. 3 factorial is 1 into 2 into 3, that is 6 by m cube. Mu 4 dash is 4 factorial by m raised to 4. 4 factorial is 1 into 2 into 3 into 4 by m power 4. Then 1 into 2 into 3 into 4 is 24. 24 by m power 4. Thus the third and fourth central moments are 6 by m cube and 24 by m power 4 respectively. Now using the first 4 row moments, we can get the third and central moments, third and fourth central moments using these relations. The third central moment is given by mu3 dash equals 3 mu2 dash mu1 dash plus 2 mu1 dash whole cube. So when we substitute the various row moments in this equation, it is 6 by m cube minus 3 into 2 by m square into 1 by m plus 2 into 1 by m cube. So these are the equations we have obtained by putting r1, 2, 3 in this general moments equation, that is mu r dash equals r factorial by m power r. So when we simplify this, we can see that here is a common denominator m cube. So we can see that this is 2 by m cube. Likewise, this is the equation for the fourth row moment, fourth central moment in terms of first 4 row moments. So mu 4 is this. So 24 by m power 4, 4 into 6 by n cube into 1 by m, which are the values of mu 3 dash and mu 1 dash. Then 6 by m square, 6 into 2 by m square into 1 by m square minus 3 into 1 by m power 4. So you can cancel some similar terms here. So it is 9 by m power 4. Thus the third central moment is 2 by m cube. Fourth central moment is 9 by m power 4. Now let us see the skewness and kurtosis measures. The skewness measure based on moments is beta 1 mu 3 square by mu 2 cube. So when we substitute this mu 3 and mu 2 in this equation, that is mu 3 from here 2 by m cube, mu 2 from here 1 by m square. So when we substitute those equations, we get it as 4. Now gamma 1 is root beta 1, which is equal to root of 4, that is 2. So we know that this value of gamma 1 is always positive. It's not only positive, it's fixed as 2. It cannot be changed. So 2 is greater than 0 Therefore, the frequency curve of exponential distribution is always positively skewed. That is, it is always positively skewed. So it is unlike that in continuous distribution, normal distribution we discussed. In the normal distribution, we found that the frequency curve was symmetric, but here the frequency curve of exponential distribution is positively skewed. Now, this is the measure of kurtosis. It is beta 2 mu4 by mu2 square, that is 9 by m power 4 divided by 1 by m square whole square, which is 9. Now that is gamma 2 beta 2 minus 3, which is 6 greater than 0, and this frequency curve of exponential distribution is leptokurtic. Now we can see the different graph of exponential distribution for different values of m. We have drawn here for values of m like 0 0.5, 1.0, 1.5 and 2.5. You can note that when m is 0 0.5, it is starting from 0 0.5. We can see in the equation, this equation will be f of x equals 0 0.5 into e raised to minus 0 0.5 x, that is m e raised to minus mx, m e raised to minus mx. When we put x 0 here, this is e raised to minus 0 0.5 into 0, which is e raised to 0.5 into e raised to minus 0. E raised to minus 0 is 1. Okay, therefore it is 0 0.5 only. So that is why the graph has a starting point 0, the value 0 0.5. So this is for 0 0.5. Likewise for 1 it will be starting at 1. For 1.5 it will be starting at 1.5 and 2.5, and everywhere we can see the graph is coming down with a positive skew. Okay, the skewness is positive here because in the initial values only we have the higher probabilities. Thereafter the graph is coming down and merging with the x-axis. That's why the frequency curve is positively skewed. Now, this is a very important property of exponential distribution known as memoryless property. Here, we consider a case of waiting time for occurrence of an event. That is, for this, to interpret this, we consider an instance of waiting time for the occurrence of an event. We found that the waiting time for the occurrence of an event will follow exponential distribution. Now, suppose the event has not happened after k years of waiting. That means you have installed an electronic device in a circuit, and we are waiting for the day of installation onwards this failure of the event. And suppose the system, that unit was working for the last k hours. So when another person joined with this customer, the second person also waiting for the waiting for the failure of the unit. So there are two persons. One person is waiting from the time of right installation onwards, and the second person is after k hours its usage. So there are two variables, each variable for the waiting time, and one is related to the first time of installation onwards. The second variable is related to after k hours waiting. Now this property of lack of memory shows that both random variables have identical distribution. Both x and y are identically distributed. That is, x be the waiting time for the device will go on fail to function from the time of installation onwards. That is the moment we started the game, or the moment we started the experiment. Suppose the device not failed after k years, then y the waiting time after k hours. So y is equal to x minus k. That is, after a usage of k hours, after a consumption of k hours, y is the waiting time. So the memoryless property states that both x and y have same distribution. This means that the k hours use not considered in the future, the waiting time for the occurrence of the event. That's why we say this property memoryless, that is the wear and tear due to k hours use, not considered for the future waiting time. So we say the unit forgets its fatigue and functions like a newly installed unit from the time of k from the moment of after k years. So this is stated in the following probability equation, that is y greater than or equal to t given x greater than or equal to k equals probability of x greater than or equal to t. That is x greater than or equal to k means till k hours usage the unit not failed. What is the probability of this lifetime is greater than or equal to t. So probability of y greater than or equal to t given, that is known that not failed after k years use. This probability is equal to probability of x greater than or equal to t. This x represents the lifetime from the moment of installation onwards. Therefore, probability of this y greater than or equal to t, that's after an interim duration, after a period of k hours use, is equal to probability of x greater than or equal to t. And this k hours usage, that k hours function of that unit not coming is not present in the right side probability. That doesn't appear in the right side probability, which means that the k hours not considered in this equation, or that k hours consumption already forgotten. That's why we say this lack of memory property of exponential distribution. And this property has made a lot of applications for exponential distribution in reliability theory. We are not coming to the proof of this result. We want to know only this property of exponential distribution. Thank you.